name is John Delaney. I know that many of you had lots of other opportunities for many other things tonight, and some people have said, my goodness, you know, it's just that much money for one professor. I promise you that you'll get your money's worth, and we will have an intermission at about 11 o'clock. And I think you should all be in bed by at least 1 o'clock in the morning. So what this title is almost impossible to really deal with effectively, and I'm trying my hand at it because I think many of us need to begin embracing the opportunities that we have to protect the ocean, to become familiar with the ocean, and begin to actually understand the ocean in much, much better ways. And so that's part of what I'm doing. And I have sort of a three-part presentation. The first will be focused on the way human beings have interacted in different modes with the ocean. And then the middle portion will be this project that many of us here at the university are involved in, which is building a fiber optic network offshore Washington, Oregon, to understand the ocean in totally new and different ways. And then at the end, I'll try to take a somewhat dangerous but energetic look into the future, what might be possible. And I'll mix a little philosophy, maybe the odd poem, and some music along the way. So this isn't your standard scientific lecture anyway. It's a mixture of things that turn me on, I guess, is the best way to put it. But the ocean and the relationship between human beings and the oceans is one of the main elements of that excitement on my part and on the part of many others, I might add. And I urge each of you, if it suits you, to become more proactive on behalf of the oceans, because as I tried to develop in the first lecture, the oceans are the life support system for the entire planet. And those of us that live on the continents and walk around on our hind legs aren't that intimate with the ocean. And so it's an interesting opportunity that we have in the next 5 to 10 years to become much more intimate with the ocean through, dare I say this, through the magic of technology. And that would be a key part of what I'd like to develop here with you. The focus of the last lecture was on the 15th was human culture. The focus of this lecture is the question, what paths technology, science, oceans, and humans? And of course, no one can answer that. What I'd like to do is at least let's open the dialogue and begin talking about it. And it really is a dialogue. Perhaps all of us will be involved. The next one is focusing in more so on a fantastic discovery that took place about 35 years ago of the fact that volcanoes without sunlight support life on this planet, and we are beginning to suspect it might be true on other planets. And on the 20th of May, I will sit here with John Barros, a colleague of mine and a professor here at the university, and talk about life deep within the planets, and then life beyond, possibly life beyond Earth. So those are the elements. And then, because a number of folks in the audience here and myself will be at sea for a large fraction of the summer building this cabled observatory, which you're about to hear about. I will come back in November. We get back on shore the end of the first week of October. We leave on July 13th, and we come back on the end of the first week of October. So by November, I will be able to report to you what we have done with 82, 83 days at sea, building this system, which is paid for by the National Science Foundation. So that's the sort of the menu, I suppose. Today, this is the topic, and it's interesting for us to think about what has gone before and talk about what might be coming. So one of the things I wanted to start off with is just talk a little bit about how human beings relate to the global ocean. And we do that in many different ways. And I can't capture all of them, but I've captured 6 threads here. And I'll try to weave some of these together during the talk. So stewardship and ethics, arts and entertainment, and there are many aspects to that. I'll focus rather simply on science and education, but I and a number of folks in the audience could talk for hours with you about that. We will talk about resources and hazards. We will then talk about trade and commerce, not very much, but a little bit. And then the role that warfare and defense has played in bringing us into the ocean and allowing us to operate within the ocean is more than you would have hoped, I suppose. But it is a consequence. A lot of what we can do within the oceans now is a function of things that happened during the Second World War and since. So stewardship and ethics, let's think a little bit about that. All of Washington, which is on the western edge of the continent, all of the Pacific Northwest, these factors, agriculture, water, wildfires, hypoxia in the ocean acidification, and fisheries, all of these, in one way or another, are related to the Pacific Ocean and the climate variability and the natural variability of the ocean off of our shore. The ocean is the engine that drives much of the weather patterns that Cliff Mass talks to you about. Remember, the ocean, in the upper 2 meters of the ocean, there's more total heat than there is in the entire atmosphere. And the ocean is, on average, about 4,000 meters deep. In some cases, it's 11,000 meters deep. But 2 meters of the ocean contains the same amount of heat as the entire atmosphere. So the ocean is the engine, basically, that runs the planetary climatic system. Whether you're on land or at sea, variations in the ocean can trigger drought, can trigger rainfall, can trigger all sorts of complex weather. I'm not saying all weather is related to the ocean, but all weather is indirectly driven by the energy from the ocean. Now, this is a picture of dawn in Beijing, and it shows some of the issues that we face in terms of CO2 and pollution of various types in the atmosphere. Ocean acidification is related to the ocean's daily uptake of about 22 million metric tons of CO2, and that has a very significant impact on the chemistry and the biology of the ocean. Now, I'm going to show you an equation, so hold on to your seat. The interpretation of the equation is in the 3 circles, but the equation itself is just CO2 as a gas going into the ocean, and the combination of the water and the CO2 with carbonate, ion, which exists in the ocean, results in bicarbonate, which is a weak acid. So the more CO2 that goes into the ocean, the more the ocean becomes a little more acidic in this fashion. And when that happens, things like the beautiful shell on the left begin to degrade, and they eventually wind up, the false color image on the right looked like the one on the left. This is something that we are struggling with even now, and industries on the west coast of Washington, in fact around the world, are beginning to see impacts in terms of the dissolution of carbonate shells of simple animals that live in the ocean, as well at the base of the food chain, as well as larger animals. Hypoxia, which really means the lack of oxygen, has been a routine pattern off of our coast for about the last 20 years. We don't quite understand it, but we do see what it does. And so we need to study it more thoroughly in the ocean. We need to be in the ocean in order to study some of these processes. But these dead zones, they occur offshore Texas, Mississippi, Louisiana as well, and there's lots of discussions about how it comes about. Everyone is familiar with what happened in the Gulf on April 20th, 2010. There was an explosion, and the Deepwater Horizon oil rig began to spill around 210 million gallons of oil into the Gulf. bad news. It wasn't even the worst of its type. There were other spills, and there will be other spills. We need to learn what the impacts are, and we need to learn from within the ocean how these things unfold. This is a beach. This is a beach on the island of Midway. And you can ask yourself, well, this is one of the products of the human culture. When I was in the Galapagos Islands in 1970, I was shocked to see on the shoreline a Clorox bottle. But I was naive at the time, and in fact, wherever you go these days, there is plastics in the ocean, and it may be in the food chain. You may actually have either eaten fish that have plastics in their alimentary canal, or you may have ingested very, very fine particles. This is a picture produced by Nikolai Maximenko at the University of Hawaii, in which he did a model of what happens to plastic as it goes into the ocean. It tends to wind up in those gyres. I don't know if you remember last time I talked about the gyres in the ocean. Well, the gyres are basically, it's hard to say it's a gigantic whirlpool, but it does circulate at the scales of thousands of kilometers. And as it circulates, the particles tend to move inward, and they tend to be isolated in the centers. And that's what these concentrated garbage patches look like globally. So what do we do about this? What do we do about all of this? This is part of the responsibility, the stewardship that we have to look after the ocean itself. And each of you needs to spend a little bit of time, I hope, thinking about what role you could play in making a difference in one or the others of these. If you hadn't thought much about what it's like to be an albatross, here's a good view of a relatively happy albatross with a chick underneath it. I frankly can't tell male and female albatrosses apart. But this one has a tag on its right leg. And there are other albatrosses which are fed by the parents, some of them tiny, and many of them don't survive, and the chicks are fed by the parents, bringing the parents range widely. If you haven't seen an albatross flying, they have up to a 12-foot wingspan. And you've all heard of the rhyme of the Ancient Mariner, the reference to the albatross around the neck of the mariner. It's a lot of symbolism there, but here's what happens to some of them. This is a dead one, clearly. But when you look at the gut contents, it's full of plastic. And this is not an isolated case. There are many, many of these. Chris Jordan spent quite a bit of time in Midway photographing all sorts of aspects of the situation. But this is just emblematic. It's emblematic. And I would say to you also that plastics are sort of an iconic issue rather than a fundamental, devastating situation at this point. But it is iconic in that, in one way or another, we are all complicit to the fact that there is a significant amount of plastic in the ocean, and more all the time. And it's probably something on a lifetime scale, or maybe even generational scale, we might be able to do something about. So let's come back to that. I'm not overdoing this, but I don't want to underdo it either, because it is, as I said, it's an iconic issue with regard to the ocean. If you can't see CO2 going into the ocean very well, but you can see plastics showing up in the ocean. And there's some evidence that plastics go up through, very, very fine-grained plastics, go up through the food chain, and eventually you might consume sushi with plastic or something of that sort. So be aware that what goes around comes around. Now, let's shift over to arts and entertainment. There are many, many ways. Last time I used classical music to discuss some issues and to emphasize others, and just for the sheer joy of having a lecture in which I could play some good music I liked. But also there is art that almost everybody knows about. Everybody has seen this, again, absolutely classic piece of art by Hokusai, and it is probably the best known piece of art, Japanese art anyway, in the world. Almost everybody has seen it. but somebody with not quite a sense of humor, but with a message that they wanted to share, actually took advantage of it with regard to plastics in the ocean and came up with this title, What Goes Around Comes Around. This is from the Bozeman Gallery. Well, in 2010, I was invited to participate in a cruise in the Galapagos Islands with a number of folks because Sylvia Earle had won the TED Prize, and she asked that everyone do everything they can to preserve and save the oceans. And somebody walked out of the audience and handed her $1 million check and said, do something to galvanize people into making a difference. And Sylvia decided to have a party. And there are a bunch of us that were invited for various reasons. They had 20 scientists, a number of folks from Hollywood, a number of folks from Wall Street, a number of folks from a variety of places. About 100 people on board a ship that was the Endeavor, and it's the National Geographic ship. And so it was a really amazing trip. It was about 7 days. And I met a fellow that I didn't know much about, but I had liked his music. And I don't know if some of you may even be familiar with it. He wrote and sang Running on Empty and a number of others that the Eagles made popular. But there were a number of interesting people on this cruise, and some of them were very passionate about the ocean and moved into a form of art in order to express both their frustration as well as their resolve to do something. And in Jackson Brown's case, his wife was a major player in the studying plastics in the ocean. And he began writing a song during that cruise. And I want to share that song with you, partly because I've introduced the issue of plastics, not because what we're going to talk about later is going to instantly solve the plastics problem, but because, as I say, plastics are an iconic or emblematic issue of what's going on in the ocean. So I'll be quiet here for a bit, and let's just listen to what Jackson has to say about the ocean. something to think about. The use of art, the use of it in a form of poetry to emphasize, and people have used protest songs for a long time in various ways, but it's something to think about. The ocean is our life support system, and it is not faring well at our hands. And that actually is an issue that will affect us all. So science and education, I will say only one simple thread here. The question is, as you look at some of the things we've discovered in the last 35 years, and we'll be talking about this next lecture, a question arises, how did life begin on Earth? It certainly didn't begin in a warm, shallow pond like Darwin suggested. And the question is, where might it be elsewhere? What might be the origins? And at some level, what might be the limits to life? One of my colleagues here in the audience, Deborah Kelly, has spent a lot of time studying the limits to life in systems like this, where this is a black smoker on the deep sea floor at about 1,500 meters depth, and it is putting out fluids that are right at the boiling temperature, around 340 degrees centigrade. That's what you're seeing, is some evidence of the boiling reflecting the lights from the camera. So it's a beautiful picture, but it also raises philosophical, scientific, educational, and even ethical issues when we start looking at going to other planets. Should we go to other planets and run the risk of contaminating them? If we bring anything back from other planets, will it contaminate us? There are any number of issues related to life on Earth and life on other planets. Some of the moons of Jupiter have the potential, and of Saturn have the potential of having these types of systems on board. And I don't know if my children will be involved in the exploration of it, but probably grandchildren and certainly great-grandchildren are liable to be visiting other planets looking for life of various types. We will be well served by studying the opportunities we have here on Earth to understand that better. Resources and hazards. We've looked at the oceans from the point of view of resources and hazards for many, many centuries. Resources of various types, the obvious ones are fishing. You remember I talked about eastern boundary currents in the first lecture. The blue arrows represent eastern boundary currents, and there are 6 or 8 systems similar to the one off Washington, Oregon, California, which is called the California Current. And they are around the world on the eastern side of oceans, right up against the western side of a continent. So, and a very large fraction of the marine fish catch, which many of you have eaten, correlates with the eastern boundary currents. Another phenomenon that the ocean harbors, as do the areas in the Arctic and the tundra, there is an abundance, I suppose is the best way to put it, of gas hydrates. Now this is a somewhat dated figure, but gas hydrates have been found on the seafloor. One of the cable elements that I'll talk about, we have gas hydrates in the area, and some of the samples from there in the hands of Bob Collier from Oregon State, shown here, can be lit and burned, and it's quite a clean flame. It produces only water and CO2. We're trying to study gas hydrates as a possible energy source that is much cleaner, say, than some oils, some petroleum products, and even natural gas. It burns even more cleanly. Hazards, not resources, but hazards. The undersea megathrust takes place where a tectonic plate is thrust under another tectonic plate. Usually that happens when an oceanic plate actually is thrust under a continental plate. And in the last 10 years, since 2004 in the west coast of Sumatra, there was a major earthquake, and you remember the big tsunami. Then in 2010, the magnitude 8.8 in Chile, and then the most devastating, at least visibly, if not in terms of human lives, was the one that took place in Tohoku Oki in Japan. Now, we have a similar system just off of our coast, and I'll talk more about the Juan de Fuca tectonic plate. But a question that we need to address is, well, what are we going to do about that? Well, I'll talk a little bit later about it. This is a picture put together by folks at PMEL NOAA of the energy, actually the rise height of the water radiating out from the Tehukuoki earthquake across the Pacific. And you can see in the scale bar on the right-hand side that the reddish patterns surrounded by yellow are in the range 20 to 30 to 40 centimeters height. But these are big waves, and they come all the way across the Pacific. And it's not a simple wave. That's the point here. The energy that's involved is, in effect, proportional to the color scale here. There's a key point to be made, and that is the most dangerous tsunamis are not the ones that occur across the ocean from us. We have plenty of warning capability. The most dangerous tsunamis are the ones that occur triggered by big earthquakes that are near shore within 10 to 20 minutes of transit time for the tsunami. Not very much warning time, and the intensity is huge. So the time will come when such an event will take place off of our coast, as it did 314 years ago. And the recurrence interval, best estimates of the recurrence intervals for this area are in the range 300 to 500 years. I'm not trying to scare anyone, but I am saying, why not spend time trying to figure out how to diagnose ahead of time when such things might happen and put things in place that might give us warning or at least allow us to thoroughly study such an event. I think that could happen off of our coast. I'll come back to that. The tsunami in Japan, amazing. It was amazingly destructive. But the superstorm Sandy also left behind a swath of destruction, and it actually flooded the New York subway system, I think for the first time. And these may become more common. We don't know. But the bright side is it could have been much, much more destructive had there not been these elegant predictions of what the path would be and what the effects would be. So it's not like we're starting from square one. We have some considerable skills in terms of addressing these things. One hit in 1999, one hit Seattle and the Pacific Northwest. I don't know how many of you remember it, but it came in fast and it blew up awfully large, and it left behind a couple iconic images, and one of them is this one, which is Interstate 5 near Chehalis. We are not immune to what happens in the ocean, comes ashore and hits us. Almost everything that we experience onshore came from the ocean off the coast. Briefly, shipping is a major, major industry. Those patterns of transit are shown, and it's unbelievable the amount of goods and materials that are shipped by the ocean. A very large fraction of the total amount of trade takes place on the planet through shipping containers of various types. And the newest versions, here's a version of a new ship that's just been designed. It's going to run on liquid natural gas, and it's got something like 9,000 of these. The TEU is a 20-foot equivalent unit, which is basically the containers that you see down in the port of Seattle. 9,000 of these things. I saw a few ships that had 12,000 of these things on board. So these are new designs. We're not backing away from this, and yet this type of activity is responsible for releasing, either on purpose or by accident, a significant amount of fuel into the global ocean. Warfare and defense. Now, this is not a topic that I'm altogether facile with nor entirely comfortable with, but I will tell you that the consequence for oceanography was profound, and I will try to share some of that with you. The consequence for us during the First World War, Second World War, and certainly the Cold War was that we used the oceans as a barrier, a defense. We haven't been invaded, and the ocean has served as both a buffer and a moat, so to speak. The little lumps on the top of the conning tower there are human beings. So you get a sense of the scale here. the most complicated machine on the planet is probably a nuclear submarine, and they are very stealthy. And it's that stealth that is mostly responsible for the SALT treaty with the Russians, because they simply couldn't be found. So that's the military side. But the consequences. What's the effect of warfare on ocean technology? Behind in gray, you see the Atlantis, the ship out of Woods Hole, Oceanographic Institution, and I'll show it more clearly, but the submersible Alvin is hanging from the A-frame over the water. It was first used in any serious way in 1966, when it actually located twice a lost nuclear bomb. It was a result of a collision near Spain, and it found it first in about 780 meters of water, and then as they tried to recover it, they dropped it, and it went downslope, and they went back down and found it again. And so Alvin has been very significantly involved. It's named after Al Vine, an engineer from Woods Hole. Long stories, search on Alvin submersible and you'll read some great stories. It is also the key platform that we used as a community in 1977 to explore some of the ideas that folks had about where unusual events were taking place on the seafloor, and it's responsible for us finding near the Galapagos Islands the first submarine hydrothermal vents. And that was a very exciting discovery, and in the last 35 years it has played a powerful role in exploring the seafloor in many locations. It was built by the Navy, it was supported by the Navy, it is owned by the Navy, and it is used by scientists. And it has a great record. And again, my colleague Deborah Kelly here was for 5 years in charge of the academic committee that oversees the use of Alvin. So this is what it looks like. It was taken by Mitch Ayland, and it is a beautiful, beautiful system. I can stand up in it, but barely. It's a titanium hull about 2 inches thick, and it has a few small windows that are very, very hard for a 6'3" person to get down and look at, unless you can stand on your head. And being in there for 8.5, 9 hours is a challenge. But it's an amazing system, and we've used it a great deal here. We now use other systems which we can talk about later. I want to switch now to a woman named Marie Tharp, who worked with Bruce Heason, who was a PhD geologist from Lamont Doherty Geological Observatory in Palisades, New York, right near New York City. And she took the data that Bruce was able to accumulate as a result of Maurice Ewing's effort. Maurice was the director of Lamont at the time. And she interpreted all the records and came up with a pretty good idea of what the shape of the seafloor looked like. And here is the map. It is a painting. And it has turned out to be unbelievably accurate. And it took a very long time, and Marie actually mixed science and art in order to produce one of the most powerful insights into the planetary distribution of what we call bathymetry, or the shape of the seafloor. But this was very powerful, and it fed into the evolution of plate tectonics. Early stages of this were produced in 1966. And another thing that the Navy was very, very interested in, and I'll show you why in just a minute, was a map of seamounts. Where are the seamounts? Because if you have nuclear submarines that are charging around in the ocean at pretty fast rates, they wanted to know, where the hills were. So a huge amount of energy went into mapping them, and there's tens of thousands of seamounts, which are all little volcanoes. Remember that. Volcanoes are more important than any other aspect of the entire planet. But so the map of the seamounts is here, and the Navy was very pleased with that, except that every now and then they ran into one that nobody knew about. And that was an odd way to map. They don't want to do the mapping that way. But this is the result of what the hull looked like after it impacted a seamount that wasn't there. And then finally, mapping the seafloor. How do you map the seafloor? Do you realize that we have much, much better maps of the moon and Mars than we do of the seafloor? Some wag some time ago said, and forgive me if it seems slightly off color, but they said, you know, we know a great deal more about the moon's behind than we know about the ocean's bottom. And it's true, because the ocean is impenetrable when it comes to electromagnetic radiation at a distance greater than 100 meters. Whereas when we map other planets, they don't have water on board, and so we're mapping the surface of the planet, and we can do it from satellites or to spacecraft, and we can use laser altimetry and all sorts of other excellent ways of doing it. You can't do that on the ocean floor. So the guy on the left began mapping the seafloor in, he's using the same technique that was used in the Challenger expedition, which is a lead line. That's a heavy lead weight on the top of the thing. He's whirling it around. He's going to throw it away from the ship, and it will sink to the seafloor, and they will mark on the twine, marking on the twine, how deep it went, and that's how they would judge how deep the water was. And imagine, imagine the guys on the Challenger expedition in 1865 when they got to the Marianas Trench, which, and they thought it was only 8,000 meters deep. That's 8 kilometers. So imagine handling this system when the water depth is 8,000 kilometers. It took a day to get one measurement. One measurement. Now, we have new ways of mapping the seafloor in which we can make 300 million measurements in about an hour. It's unbelievable how far we've come. And in the last 20 to 30 years, it's an exponential curve of our ability to map the seafloor much, much better than we ever were able to before. The ship that you see in front of you depicts one of the techniques. There are many others, and some of them are on what we call autonomous underwater vehicles, which are little pilotless robots that can fly around on a pattern. They can take a pattern like mowing the grass on the seafloor, and they map and they map and they map and they map, and then they run out of battery power and they come to the surface, charge them up, download the data, plot it, and then it goes back in. And so those are really elegant. Furthermore, at this point, it's quite exciting that we are able to map not just the seafloor, but we can map the ocean itself. And so some of the venting of gas hydrates, bubbles of methane, come up through the ocean, and we have techniques that can not just map the seafloor, but simultaneously map what's going on in the ocean. That's a very, very powerful approach as well. All of these pioneered by the Navy and eventually delivered. Now, I want to show you something that's very elegant. This is the interior caldera, the floor of the caldera in blue and yellow. The edge of the caldera is in red, and it is 150 meters shallower than the floor of the caldera, okay? And what you're seeing are those lobate patterns are lava flows. So the mapping technique, using one of these autonomous underwater vehicles with high-resolution bathymetry, was able to map out these lobes of lava. And then in 2011, April, this same volcano where the yellow part is there erupted again, and I'm going to show you the mapping that it took place afterwards. And you're seeing 2 or 3 meters at a depth of 1,500 meters. You're seeing 2 or 3 meters of relief that's picked up because it was mapped again. It had been mapped before, and then it was mapped again. Watch. You see that blue lava flow, that blue lobate zone? That's a lava flow. You're looking at the amount of lava, 3 to 5 meters thick, that was added to a volcano. So we now have ways of using techniques that have been developed by lots of different folks, but certainly partly supported by the Navy, to map the seafloor in unbelievably elegant ways. That really turns me on. And then finally, plate tectonics. You've all heard about plate tectonics, but the Navy spent quite a bit of time during the Second World War trying to find German and Japanese submarines, and they did it by towing magnetometers behind them. And they found, as they began towing whole areas, they found that there were curious patterns of magnetic anomalies on the seafloor, and they looked a little bit like what I show you on the right-hand side there, which is just off of Vancouver Island. And it was a pattern. It was a very consistent pattern, and that has been colored in now because we were able to interpret the ages of the sea floor based on dating other rocks from other places. And the magnetic anomaly, the magnetic field of the Earth switches. And as it switches, then the magnetics of the rocks on the sea floor reflect whether it was North Pole to where we now call it the South Pole, but the magnetic field reversed and then went back and then went back and went back. So what we call the North Pole was actually the South Pole. Sounds complicated, but the fact is the rocks remember. And by interpreting these rocks, we began to find out that the seafloor must have come apart. This was in the 60s, the 50s and 60s and 70s. And that contributed on the left-hand side to the interpretation that the seafloor was pulling apart at about the speed your fingernails grow. And very shortly afterwards, looking for folks who were breaking the Nuclear Test Ban Treaty in the 50s and 60s, they recorded earthquakes all over the world, and they found patterns of earthquakes that were in places like beneath Seattle and beneath Japan and beneath the Aleutians and beneath South America, the Andes. And lo and behold, the two pieces fell together because of the Navy doing different kinds of studies and different groups looking at different technological issues that were defense related, I suppose you could say. And that allowed us to unravel plate tectonics. Now, I'm not suggesting that we keep up the pattern of let's stay at war because we can make giant discoveries. I'm simply saying that these are spin-offs.